I'm going to be going over that again myself and upload. I'll give you another example of that because I inadvertently forgot to record that part of the session. So I'm going to do that again later on for people that weren't here. And I'll do a couple of examples again like we just did so you get another look at it since you guys were here. Okay, so, but I'll have to record it again later. Okay, so let's take a look at some of these questions. Complete the conditional, but this is quiz 3, which has already been due, so you at least saw the answers for this. Complete the conditional proportion table, solve the problems. Overall, what percentage of surgical patients was discharged delayed? Okay, so we're looking only for surgical patients here, right? So overall, how many surgical patients were delayed? Okay, discharge delayed in a small hospital, a large hospital, for major surgery, for minor surgery. They're looking for everybody. So we would add all of the surgeries, right, that were delayed, 70, 12, 15, 24, and put that over all of the surgeries that were performed, 700, 200, plus 60, plus 300, to get a percentage. Now, I'm not going to bother to actually work that out, but that's the way that you would probably do that. I didn't see too many people having an issue with that. Okay, complete the proportional table, use it to solve the problem. Okay, so what we're interested in here is the total number of, this is what I mean by Blackboard doing this funky stuff with overlays and stuff like that. The table. I can't tell what that I'm going to have to open up Blackboard. Can't tell what that says. Okay, quizzes. Quiz 3. Okay, no, actually, run it through. Okay, partially completed table gives relative frequencies of data. That's percentages rather than the actual numbers of people. Residents, retirement. What percentage of resident males are over 79? Okay, well, the first thing we need to know is we're only interested in males, right? That's our conditional probability. We're only interested in males. What percentage of males are over 79? Well, we know that 1/10 of a percent are between those two ages, and 11/100% are between these two ages. So 0.21 of the total population is over 79, but we're only interested in the males. So we have to add up the total population for males and put 0.2, I think it's easier for me to just bring up my notepad and do some of this. And I'm going to be selective about which ones I do. Okay, so in this case, I know that the total proportion of males that we're talking about is the male proportion of the population is 0.19 plus 0.1 plus 0.11. Okay, so that's 30, that's about 40% of the population was male. So what percentage, did I get everybody? What percentage was over 79? Well, it's just these two groups, which are 0.11 and 0.1, or in other words, 0.21 over 0.40. That's the proportion of males that were over 70 years old. What proportion were over 79 is actually what they ask. That would be 0.11 over 0.40. Okay, so I think you guys are pretty solid on that. So I'll move on. Stop me. Are we also able to go back and look at our old quizzes? That's a good question. What I'll do is I'll post I believe you can, and it should show you whether you're right or wrong as well. Plus, there's an answer sheet that shows you, if you go into Blackboard under the quizzes, there's an answer sheet for each, except for quiz 4, which will be posted shortly as soon as the due date is passed. Okay, so let's see. Complete the conditional proportion table. Use it to solve the following problem. It's the same outfit. Percentage of residents that are female in the age group 79. It's the same deal. We would add up these proportions, come out to 60% of the population is female, and only 20% of the population of females is over 79. So that would be 0.2 over 0.6. Okay, so we should be okay there. That's what percentage of females? 0.2 over 0.6 is a third, right? Where are they? Oh, I'm sorry. What percentage of the residents are over 79, which is going to be 0.2 over the entire population, which is 100%. So it would be 20%. Yeah, you caught me on that, Isabel. Find the indicated probability. A group of volunteers for clinical trial consists of 81 women, 77, 18 of the women, and 19 men with high blood pressure. If one of the volunteers is selected at random, find the probability that the person has high blood pressure, given that it's a woman. Okay, so now, first condition we have is that we're only going to consider the women. And there's 81 women. Of the 81 women, 18 of them have high blood pressure. So the men aren't even being considered. So the probability of selecting someone from that group that has high blood pressure is going to be 18 over 81. Everybody okay with that? Stop me on the chat box if I'm messing it up, or if you need me to go over it a little bit more carefully, or actually do the solution. Find the probability group of volunteers for a clinical trial consists of 83 women, 78 men. 21 of the women and 20 of the men have high blood pressure. If one of the volunteers find the probability that the person is a man, given that they have high blood pressure. We kind of twisted it around a bit, right? So we know how many people in this population have high blood pressure, right? We have uh, uh, 21 women and 20 men who have high blood pressure. Okay, if one of the so we have 41 people with high blood pressure. If one of the volunteers selected at random find probability the person is a man, given that they have high blood pressure. Well, now we're only counting people that have high blood pressure. The population we're dealing with is 21 women, 21 women and 20 men. So we have 41 total population, of which 20 of them are men. So the probability of picking from those 41 people with high blood pressure, picking a man, is 20 out of 41. 20 over 41, right? A little less than 50%. The table loads smoking habits of a group of asthma smokers. What's the probability that a woman is a non-smoker? So how many women are here? 516. How many of them are non-smokers? 363. So it's 363 divided by 516, right? First define what the population is that you're working with, right? Your condition. First, make sure you're only looking at people that satisfy that condition, and then look at the particular group for the proportion that you're interested in within that group. So 363 out of 516. Describe smoking habits. So again, what's the probability that a light smoker is a woman? So we're only interested in the light smokers. And it looks like out of 130 light smokers, 65 are women. So it's 50% chance of, excuse me, wait a second. What's the probability that a light smoker is a woman? So there's 130 light smokers, 65 of them are women, so it should be 50%. There we go. I didn't see it down there. Okay, now this is an interesting one. We're starting to get into our diagnostic tests to some degree. Okay, or kind of border on them. Table below on blood type and gender show how to find probability. A person is male given that their blood type is A. Okay, let's see. We're only dealing with the probability. Well, first of all, let's see if this is set up quite right. The probability that they're male, given that their blood type is A. Okay, so first of all, we're only dealing with people that have blood types of A. right? So that's going to be 0.226 and 0.0177. So those are going to be on the bottom of our ratio, right? That's going to be our denominator. So those two values are going to be our denominator. So the only one I see that has that denominator is going to be this one. And just to check it, the probability the person is male is going to be that probability as your numerator over that as your denominator. So clearly we even didn't even have to go that far, right? We're able to tell that right away. Okay, for a particular test, the sensitivity and the specificity are 0.96 and 0.93. Suppose that the prevalence rate of using a specific drug was actually 0.3. Calculate the probability an individual actually is a drug user given that the test is positive. So we want to calculate the positive predictive value here. So I'm going to go, this is a little bit more complicated, so I'm going to take the closer look at this one. I'm going to give you two ways that you can solve these problems, right? And one way is my kind of goofy, kind of build your own population way, which I think a lot of people kind of find a little bit easier. And in fact, it might be a good way to check your work if you use the formula. Okay, so this is going to be the test is positive, test is negative. This is going to be drug user, yes, drug user, no. Okay, so let's see what we have here. I'm gonna come up with a population. I'm gonna call it a population of 1,000 people. Okay, and we know that the prevalence is 3%. 3% of 1,000 people is 30. Oops, did I miss something here? Let me go back. Yes, Jen. Regarding question 8, can we go back to it? Sure. Before I get started on this, use a table on blood pressure to find the probability a person is male, given that their blood type is A. Set up the problem, but do not solve. Okay, so let's look at this. Let's read what this says. This is kind of a slant. Usually you see this as a straight up and down line. But what the nomenclature says here, the probability a person is male given that they are blood type A, right? So we want to find the probability a person is male given that their blood type is A. So the condition is we're only looking at people whose blood type is A, given that they're A, right? So given that they're A, that means they have to be in this column. Everybody else does not have a blood type A, right? So what is the probability equal to that a person is male given that they have a blood type of A? So that's going to be a ratio. It's going to be the ratio of all the people that have a blood type A, right, on the bottom, and the number of people that are male that have blood type A on the top. So it's going to be males with blood type A over all people with a blood type A is going to be the percentage. Okay, so let's see. So the percentage of people that have a blood type of A is the sum of 0.266 and 0.177, right? So this um, um, uh, uh, approximately, let me see what that would be. That'd be like 30, about 40% of the population has a blood type A. Of that 40% of the population, only 17% are male. So the proportion, the probability that a person is male, given that he has a blood type A, is 17% over the 40%. Does that make sense? Is that a bit clearer? Still think it's the third option, right? Well, look. I got another reason why it can't be the third. Okay, good. But let me show you something here. That's a dead giveaway. It can't be the third option, right? We're looking for a probability. A probability is always a number between 0 and 1. If you look at this, add these two together and divide by this, it's going to be a number bigger than 1. So that can't be right, right? In fact, we could have picked this one out right away, right? Because we know that we're only considering the people that are A. So we had that sum on the bottom. Okay, so okay, good. Hopefully that clarifies that a bit. Okay, so let's go back to this. So the prevalence is 30%, right? So that would mean 30 people out of 1,000. or 3 out of 100. I'm just trying to keep round numbers here, so I made it 1,000. So 30 people and 970 people are not drug users. Okay, so now if the let's see, if the sensitivity is 96%, right? The sensitivity is equal to 96%. That means 96% of the time we're going to get this right. These are tough numbers. And the specificity is 93%, right? Okay, in fact, I could have used bigger numbers than this even. Okay, so let's see, 30 times 0.96, right? How often are we going to get this right? It's going to be a little sloppy here because this uses such times 30, 28.8. Okay, so 28.8% of the time, 28.8 times we'll get it right, and 1.2 times we'll get it wrong, right? It's going to add up to 30 people, right? So, and in fact, if I had made this 10,000 and this 300, right? This would be 288 and this would be 12. I'm going to do that just to round these numbers off. It works. My simplification didn't work out that well this time around. Let's do this. So 9,700% of the people, I will get a negative drug test for people that didn't use drugs. So the sensitivity 9,700 times 0.93 is my specificity, is going to be the percentage of time that I'll get that right. So I'll clear that. 9,700 times 0.93 equals 9,021. 9,021. So that means I will get this wrong. 97 minus 9,021. Okay, I'm going to subtract from that 9,700, get a negative number, and then change the sign. So this is going to be 679. Okay, so out of 300 people, out of 300 people that actually are drug users, out of a population of 10,000, out of 300 people who are actually drug users, I'll get it right 288 times. That's my true positives. Out of 9,700 people who are not drug users, I'll get it wrong and get false positives 679 times. Yeah, okay. So I made that, the 1,000 was arbitrary. In fact, I changed it to 10,000 so I would get even numbers. Okay, and the 300 was because 3% of the population is the prevalence. So out of 10,000 people, 300 of those people were drug users. Okay, so I'm going to add these together. 679 plus 288 equals 967 total positives. Okay, I'm going to add that and put that in memory. And out of those total positives, there are 200 people that were actually positive. Divide that by the total number of positives, and my positive predictive value is a little under 30%. It's going to be 0.2978. I'm going to call it 0.3%. My positive predictive value is equal to, move this over, 0.30 roughly. Okay, so I'm going to do this. This part I'm recording, so you actually be able to go over this again. But I'm going to do this another way now, which might be a little bit more satisfying. And the first thing I got to do is find that formula for sensitivity, and I think I have it on here somewhere. Let me see if I can't find it. Actually, I'll Google it. Worst comes to worst. Let me see. You will presumably the positive predictive value formula. You will have this written down, so you won't have to do this for the exam. Okay, and that should be pretty easy to find. Where is it? Let's see, where'd it go? I have it here somewhere. I want to get it right so I don't screw this up. So I don't confuse you any more than I have today. I can't find it. Why am I having such problems with this? Let's try it that way. Here we go. Okay, I'm going to drag that out here and put it into my table here so we can work with it. Oh, that won't do that. Okay, let me make this a bit bigger and move it over. Okay, here's my formula. Okay, let's take a close look at this formula. The sensitivity times the prevalence divided by the sensitivity times the prevalence plus 1 minus the specificity times 1 minus the prevalence. Let's think about that for a second. What are we really looking at there? What we're really looking at there, which is kind of disguised in all this, is the positive predictive value is equal to the true positives over the true positives plus the false positives. All the positives are on the bottom, true positives are on top, just like we did before when we divided this. You can use the slides and this will be somewhere in the lab stuff and stuff like that. You can also like formulas like this. You can also, if you want, print them onto a piece of paper, make them easier to get to, and so on. So anything that's on Blackboard is fair game. So at any rate, so this is really what this boils down to. The sensitivity, which is the percentage time that you get it right, like 80%, times the prevalence is the number of people or the percentage of people that you would get true positives for. So if you look, we just repeat that there. That's true positives again. And if you look at the specificity, the specificity is the percentage of people that you would get a negative for, right? Correctly. Well, 1 minus the specificity is the number of people that you would incorrectly get a negative for that in that case, right? 1 minus is the ones you would get it wrong, the number of percentage of people you get it wrong for, and 1 minus the prevalence would be the percentage of people that are negative, right? That would impact. So this is the false positives. So it really just boils down to this, except now we're going to actually calculate this using the problem that we were just looking at. Okay, so let me first look up all of these values. And, sometimes it's going to be easier to use the first way that I described to you. Sometimes it might be easier to use this. So sensitivity is 0.96. The specificity is 0.93. I'll write that down. The sensitivity is equal to 0.96. And the specificity is equal to 0.93. And the prevalence is equal to 0.3%. Okay, so let's fill this in. So the top is going to be positive predictive value is equal to 0.96 times the prevalence, 0.03. And the bottom is going to be, same thing, 0.96 times 0.03, again. This time we're going to add to that. This represents the true positives. Now we're going to add to that, the bottom part at least anyway, the denominator, we're going to add to the false positives. It's going to be 1 minus the specificity. Well, the specificity is 0.93, so 1 minus the specificity is going to be 0.07 times 1 minus the prevalence, which is going to be 0.97. Okay, anybody unhappy with that so far? All right, all I'm doing is plugging numbers in here. So I'm going to use my calculator to calculate this. Okay, so 0.96 times 0.03 is equal to 0.0288. Right, that's the top, over 0.0288. This is just the same thing. Plus, go back to my calculator. And I'm going to clear that. And it's going to be 0.07 times 0.97. Yes, prevalence is 0.03. Okay, and that's equal to 0.0679. All right, so that's going to be equal to 0.0288. Bring up my calculator again. And I'm going to add 0.0967. Anybody recognize these numbers? Those numbers look familiar? I lost track of them here somewhere. Right, it's about 30%. I didn't store the numbers there. I didn't write down the numbers. Okay, so what is that going to be equal to? Bring my calculator back up. They're actually the same numbers that we got before. Clear? Okay, I'm going to say 0.0288 divided by 0.0967. Okay, and that's the same number that we got before. Okay, how many of you prefer the first method? How many of you prefer the second method? Just for my own edification. Second method. Okay, good. You know, the first method is kind of handy if the numbers are nice and round, like 90%, 80%, so on and so forth, prevalence, specificity. You can really get through it pretty quickly that way. But in this case, I kind of tripped myself up because it was a little bit more complicated problem. But yeah, second problem, if you're careful and you make sure that you understand that it's 1 minus the specificity, 1 minus the prevalence, and 1 minus the sensitivity. If you get that, if you handle that carefully, handle your math carefully, then this should work. And you want to know something else is, again, if you have time, I'm not suggesting that everybody do this, but if you have time, you can do it both ways, right? Then we just check our answer. In other words, had we done it incorrectly the first time, we would have gotten a different answer this time around, right? So it doesn't hurt to be able to check your answer a second time. Let's take a look at this last question. Suppose 3% of the population were given 3% of the population in a given community of adults have attempted suicide. Suppose it is known that 20% of the community are living below the poverty line. These two events are independent. What is the probability that a person selected at random from the community will have attempted suicide and be living below the poverty line? So I'm going to leave that up to you. You guys tell me how would I calculate that? What would that be? The probability of attempting suicide is 0.03. The probability that you're below the poverty line is 0.2. If they're independent, what would you expect that to? What number would you expect to get there? Right? 0.03, 0.2. Anybody want to hazard a guess? Right. The reason why I'm beating this to death is because I suspect you might see this in a different form, and I want you to be ready for it. Okay. Any opinion there? Someone must have an opinion on that, right? Suicide, right? Probability of suicide is equal to 0.03 probability of living below poverty level is equal to 0.20, right? Well, if they're independent, it's going to be 0.03 times 0.02. It's zero 0.2, right? So it's going to be 0.006, right? 0.006. Okay, why is that? Well, since they're independent, it's just like flipping a coin. What's the probability of flipping one coin getting 0.5 and the second coin and getting 0.5 and the third coin and getting 0.5? You can multiply them out. Now, let me phrase this another way, which could turn up on the exam, which could be a little tricky. If I tell you that the probability of having red hair is 0.2, and the probability of being left-handed is 0.3, and I tell you that I do a survey of a population. I do a very large sample of a population, and I find that the probability of being having red hair and being left-handed, the probability of that in that population is let's see, is 8%. What can you tell me about the probability of being having red hair, and being left-handed? What can you tell me about that probability? Are those two things independent, given what I've told you? They're not independent. And why are they not independent? Because if they were independent, then what I would have found is the probability of being red-headed and left-handed, red-haired and left-handed, is going to be equal to 0.2 times 0.3, which is 0.06, right? Since that's not true in this population, then they're not independent. Okay, that basically, we're doing the same problem here as we did here, right? In this case, since they're independent, we know we can multiply them to find the probability of both of them occurring at the same time. But since the probability of them both occurring at the same time was not the same as multiplying the two of them together, then we can say they're not independent. Okay, so you guys okay with that? Makes sense. I want to go through one more thing. I'm going to re-record that stuff on the normal distribution. I want to go through one more thing that you covered in the lecture. We really didn't get a chance to do in the lab. We just ran, especially I think it was like the first session, and we really ran out of time on it almost completely. I want to go through two more things. One thing is, let me see here. Let me open this up again. It is previews. Where did that go? Here we go. Okay. Let's take a quick look through this. Okay, I'm running a bit longer than I expected to, but that's okay. Survey, survey. This is quiz number 4. This one is due on, let's see what day is today. This one is due tomorrow night. Okay, so I just want to run through this quickly and see if there's any issues here that you guys have with this survey. Of 1530 have health insurance. Is this a parameter or a statistic? Anybody want to hazard a guess on that? Is this a sample or a population? Yeah, yeah, we're talking about a statistic, right? Because a statistic involves a sample, right? So this is a sample. It's believed that the population mean serum cholesterol for adults is 20 years old is 196 milligrams a deciliter. Okay, population mean, is that a parameter or a statistic, do you think? Are we dealing with a population or a sample here? Very interesting. I'm not giving you the answer. Okay, so you can chat about it all you want, but I'm not giving you the answer. The infant mortality rate per 1,000 for the 50 states and District of Columbia has a mean of this standard, assuming that the distribution is normal. What percentage of states have an infant mortality rate between 5.36 and 8.60. Well, let's think about this. The infant mortality rate for 50 states is a mean of about 7 and a standard deviation of 1.62. Assuming the distribution is normal, what percentage of states have an infant mortality rate between 5.36 and 8.60? Well, how would we have to solve that? What we would have to do is we'd have to draw a normal distribution, right? Let me just sketch. I want to do a sketch. I'll leave it up to you guys to solve this, but I want to start you off with a sketch. Yeah. Whoops. Let me close this and reopen it. And that paper. So if I can get these numbers here, let me squeeze this a little bit so I can write down numbers. So we got a mean of 6.98. Standard deviation is equal to 1.62. And we're interested in the percentage between 5.36 and 8.60. Okay, so see what that looks like if I sketch it. Here's the mean is 6.98. And we're looking for 5.636 and 8.10. This is 8.1 and this is 5.36. We're looking for the area in between these two. So the first thing I need to do is find out the z-score for each of these two, right? Z1, Z2, right? And look up on the table, the area from here down is, I'm going to make up a number, 80%. And the area from here down is 20%. So that would leave in between here 60% of the population, right? So kind of like we handled the problem before, you need to find what areas are represented by the proportion of the population between these two, but the table will only give you the area to the left of a known z-score, whatever that z-score is. So you have to manipulate it a little bit and figure out what these areas are. And it's best if you draw it out. Okay, so let me move on from that. Length of human pregnancies distributed. Again, this is kind of similar, right? Mean of 268. Standard deviation of approximately what percentage of pregnancies last at least 298 days? Think about what they're asking now. They want to know how many of them last at least 200. So we're looking for more than 298. So we're looking for the area above the z-score that represents 298 days. Right, so that's to the right of the distribution. If you sketch it out, you'll see that it may be, here's the mean. The area they're looking for is above here, 298 days. So there's an area, but your table gives you this area, right? So you got to subtract it from 1 in order to get this proportion, right? So again, got to be a little bit creative. Helps you sketch it out. The nurse supervisor said that now this is one that tripped everybody up. All I'm going to say on this one is, if required, complete the task. The percentage of nurses completing the task in less than 5 minutes. Pretty straightforward, right? Normal distribution, 10. 5 minutes is on this side. So those are the fastest nurses. Percentage of nurses requiring more than 10 minutes. So here's 10 minutes, and you're looking at the area above that. The probability that a nurse has just been assigned tasks will take between 8 and 12 minutes, right? So now you have to find 2 z-scores and 2 areas, subtract one from the other. And the slowest 20%. And I can't tell you how many people thought to themselves, the slowest 20% are the people on the left-hand tail of the distribution. Got to think about that a little bit. Which ones are the slowest 20%? Are they on the right tail or are they on the left tail? Right? And I think if you got that, you'll have no problem solving this. According to 28% of New Yorkers answered yes to the question, have you ever been told by a doctor that you have hypertension? Now, I want to get to, I want to show, this is a good excuse to talk about Excel. I don't know how many of you guys are still there. We've still got 6 people here, right? That's pretty good. Um, uh, uh, so looking at question 6 here. This is an interesting question, right? 28% answered yes, that they have, that they've been told they have high blood pressure. In a group of 10 New Yorkers selected at random, what's the probability exactly 2 of them would be hypertensive? Right? We have a similar one down here. It's the 58% are sedentary lifestyle, and so on and so forth. This is an example of a binomial variable. It's either yes, you're sedentary, no, you're not sedentary. Yes, you have high blood pressure, no, you don't have high blood pressure. I'm going to pull up Excel. Okay, and here's our Excel spreadsheet, and I'm gonna make this a bit bigger. Okay, so let's say I have 10 people, right? And I know the probability that they have high blood pressure is 20%, right? This is the probability that they have high blood pressure. This is the number of people that I'm going to sample. And I'm going to call something called successes, right? S for success, right? So I'm going to say to you, what's the probability that you'll get exactly 3 people that have high blood pressure when you sample 10 people? That's a binomial distribution. You can solve that in Excel by using the binomial distribution function. Equal binom dist parentheses. As soon as you write that, Excel prompts you and says number of successes S. The number of successes that I'm looking for is 3. The number of trials is the number of people that you're sampling is 10. And the probability of success is the probability that any one of those 10 people has high blood pressure, which is the same for all of them, 0.2. And then cumulative is whether or not you're looking for exactly that situation or that situation and any number below it. Like, in other words, 3, 2, 1, or no people have high blood pressure. So in this case, the question I asked was just what's the likelihood of exactly that 3 people? And the probability is 20%. Now, if I had said true there, right? If I had done the same thing, number of successes 3, comma, trials is 0.2, trials is 10, comma, probability is 0.3, 0.2, comma, and said true there, what it would give me now is the probability of taking 10 people and having 3 out of 10, 2 out of 10, 1 out of 10, or none out of 10. All of those possibilities occurring. And that's 88% basically, right? Much more likely. So when you use true, you find only that specific condition. When you use false, you find only that for cumulative, only that condition. When you use true for cumulative, it gives you the probabilities for all that and all the ones below it combined. Okay, so that's the deal there. Now the other thing is that when you're working with normal distributions, right, there are a number of functions that you can use. I have a list of them under the lab. There's a document that actually gives you a list of them. For instance, we have norm dist parentheses. So if you know what x is, what the mean is, what the standard deviation is, and if you say, you always say false for cumulative here, or true for, true for cumulative, right? If, for instance, I know that I'm looking for, I'm interested in what percentage of the population is below 90, given that the mean is 100 and the standard deviation is 10, and I'm going to say true for cumulative, right? It tells me that about 16% of the population, which remember that's one standard deviation below, the left of that is going to be 16%. Okay, that's the percentage of the population that is below that level. So if I do it for something on the other side, norm, this, parentheses, let's see, this time 110, right? Mean is 100, standard deviation is still 10, and cumulative is true. We'll always use true here for this particular one. That's 84% of the population is to the left of that value. Okay, now norm S-dist, parentheses. Whoops, got the equal sign. Equal norm S-dist. That's the standard normal distribution, parentheses. What it's asking for there is if you give it the z-score, it will give you the area to the left of that z-score, just like our table does. Okay, so it does the same thing. You tell it the z-score, it gives you the percentage to the left. So for instance, on this one, let's see the z-score. Let's say a z-score of -1. Okay, z-score of -1 is 15.865%, same as we saw there. Okay, now there's another one, norm inverse, parentheses. Put the equal sign in there. Oops. Okay, if you give it the area, the probability of the area under the curve, right? Let's say it's 15%, and you tell it the mean, which was 100, and the standard deviation, which was 10. This is just like using the table to give it the area, right, which was the p-value there, that first value, 15.85865, and you tell it the mean and the standard deviation. It'll take the area and turn it into the number that represents that area, 90. Okay, so 90, mean was 100, the value 90 represented the area that we just picked out there. Okay, so I'm gonna, if you look on Blackboard, you'll find that a number of these functions in SPSS, in Excel, and what it will tell you is that if you use this function, norm inverse, norm dist, for instance, it'll tell you what the input values are, what it's looking for, and what it'll give you as an output value. So hopefully that'll help you decide which ones are the ones that you want to use. Okay. Right, false because it's false. Isabel, I have to go back. I think we're talking about that previous problem that I kind of missed your chat question there. False because they are not independent, not so much continuous, but not independent. I think that's, unless we were talking about the function here. We're talking about the function here. It's just telling Excel you're interested in only that probability. Question about when you use at most, for example, at most 3, you would have 4 successes. Oh, let's think about that. Okay, the problem we just did before, we sampled 10 people, and you want to know what's the probability that you would get at most 3, right? At most 3, well, I would use 3 because at most 3 would include 3, 2, 1, and 0. If you were interested in more than 3, I would use 3 to calculate 3, 2, 1, and 0 combined, and then subtract it from 1. Right. Yeah, I think so. Okay, most 3, but what would you use? Does that make sense? There could be so many ways that you could phrase these questions. So for instance, in this example here, binomial, I'm going to try one more. If I had asked you, what's the probability that you would find, you take a sample of 10 people, just as we did here, you'll find 3 or more, right, that have high blood pressure. Right? What's probably 3 or more? Well, that's a little tricky now because using our function here, we're going to calculate 2 or less and subtract from 1, from 100 or 1. Okay, so I would say equals binom dist, parentheses, number of successes is 2, comma, trials is 10, comma, the probability is 0.2, comma, and cumulative is true. So what would that give me? That would give me the probability of getting 2, 1, or 0 people out of 10 that have diabetes, that have high blood pressure. So that's 68%. So now the probability of getting 3 or more than 2, either way you phrase it, is going to be equal to 1 minus 2 or less, right? Pretty tricky, right? Okay, so I'm going to call it a day. And I'll try and get to posting some other stuff for you, so I don't have to keep this online for too long. I want to make sure that we don't crash here as I'm accumulating video in the background. I'll re-record the beginning part, because I didn't record that, and I'll add some stuff to it as well that may help out a bit. So good luck on the test. Email me, put BIOS610 if you want me to answer questions specifically, or just post it to the discussions group. We're trying to keep up with it as much as we can. I've been last couple of days I've been staying away from the questions on the project, because I know the exam is a bit more pressing right now. Can you explain the last question on quiz 5? You guys are on quiz 5 already? Hang on a second. Let me get to that. Let me take a look at that. Quiz 5. I don't think we've posted a quiz 5 yet, have we? Oh, quiz 4. Last question on quiz 4. Okay. Okay, quiz 4. Let's go back here. Into it again. Last question. According to 58% of Americans, well, it's basically a binomial distribution, isn't it? 58% of Americans have a sedentary lifestyle. Suppose you select a sample of 12 people and find 10 of them are sedentary. In other words, another way that they don't exercise, another way of saying that they're among that 58%. So assuming that the surveillance system is correct, what's the probability that you would have obtained such a sample? Well, let's say, what's the probability, given that the probability for any individual is 58%, and you sample 12 individuals, that's your number of, let's see, equals binom this, parentheses, number of successes, number of trials, right? Okay, so that number 12 is your number of trials. Number of successes is 10 people you found that didn't exercise regularly, that were sedentary. And the probability of any individual not exercising is 0.58, right? So 10 seems like a lot out of 12 for something that's only 60%, right? So we have the probability, we have the number of trials, we have the number of successes, which is 10. So the probability that we're going to wind up is the likelihood of getting, if we say false for cumulative, it gives us the probability for that exact situation, right? Not 10, 9, 8, 10, 9, 8, 7, 6, and so on, but just for that exact situation. Suppose you sample assuming that's correct, what's the probability you would have obtained such a sample? Sounds like to me it's asking for that exact situation. Is it likely to observe such a sample if, in fact, 58% of all Americans have a sedentary lifestyle? Well, the answer to your question is going to be the answer to part A. How likely is that to occur? Right? How likely is it that you'll get something like that? Okay. Did this turn out to be 1% or 90%? So if it's a low percentage, I would say probably the answer to that is no. If you get a high percentage out of that, then I would say the answer to that is yes. The likelihood to observe such a sample, right? So really, it's just asking you, take a look at your answer there. Did it come out to be 90%, or did it come out to be 2%? Right? So, and that would basically tell you how to answer part B. Make sense? Okay, rounding. We always get that question. I would say, if you get 2/3, I would say 0.66, 2 decimal places. 2 digits after the decimal place, I think you're safe. Okay. Okay. Take care, guys. Good luck on the test, and I'll try and post some more stuff over the next day or two that I hope will help out. Take care. Bye.